All right, folks, this is the Marine Community Ecology course. This is the 5th guided demo, and this one mostly revolves around Principal Component Analyses and other multivariate ordinations. So what we can do with these ordinations, of course, is we can explore community composition and how it differs across many sites, or we can tailor the analyses to one of the many applications that we have discussed in class. So these multivariate ordination techniques, be that PCA or PCOA or whatever, NMDS or redundancy analyses, are generally our go-to tools to disentangle differences in community composition which can't be assessed by a single value like species richness. And the package in R that really does a bunch of these things for us, and that is the main workhorse for anything multivariate in community ecology, is the vegan package by Jari Oksanen. So you can go ahead and install the vegan package and then call it into your environment. You will need it today. Principal Components Analysis is the conceptually simplest ordination, but it has some requirements for the data which we have discussed in class. In principle, it requires our data to be linear, adhere to the normal distribution, with all values having decimal data from -infinity to +infinity, which is obviously very rarely the case, but that's just the sort of basic requirement. But a good example for this type of data is the morphological traits of herbivorous fish that we have played with previously, that measures like different aspects of their morphology. So you can load that data set. It is available on the website for this part and for the many parts that we've already gone through. So you can see that it has these different traits: SL, body depth, snout length, eye diameter, that we can use for a nice multivariate assessment of what these species look like. So since we generally require just numeric data, all of the analyses will only work on numeric data that we're doing today. It's often convenient to divide your data set into the two different components. So we have the metadata, which in our case was the species name and the family and whatnot. And we have the actual raw data with the values that we're interested in, such as standard length, body depth, snout length, and eye diameter. So it's really nice to separate those because it just gives you different data sets to access for your ordinations. So what I'm doing here is I'm simply selecting standard length, body depth, snout length, and eye diameter. And then I am setting the row names for this data set as well. That can be helpful because PCA kind of carries forward the row names, which can be quite useful. And then down here, obviously, to get just the metadata, you just do the opposite. You just deselect the raw data. Okay, running the PCA is very simple. Now there are several different functions and several different packages. PRComp and PrintComp are both in the stats package, which comes preloaded. There's the PCA function in the factominer package. There's duty-duddy PCA in the AD4 package, or the RDA function in the vegan package, which is the one we are going to use today. Now this one's called RDA, which stands for redundancy analysis, which is actually what it runs, but a redundancy analysis that doesn't have an explanatory variable specified or a constraint specified is just a PCA. So by running it without a constraint, it is simply a PCA. So this is how the sausage is made. This is how I run the PCA. And note the scale equals false here. This will become important in a second. So if we want to look at the output of the PCA in a quick and dirty way, we can always use this biplot function. And this is what I'm doing here. And this honestly looks terrible. And I can tell you exactly why it looks terrible. It's because we have not scaled our PCA. So we have this one vector right here that is just overriding everything. Now, if you look back a couple of pages, you might be able to figure out which one this is. But it also becomes very apparent if we just call summary herbivore raw. You can see that body depth, snout length, and eye diameter are all nice and standardized. They're actually ratios with standard length. And so they're all in their, decimals, mid-decimals, between 0 and 1. And then standard length itself has a median of 190.83, so it's much larger. And PCA naturally considers variables with larger values to be essentially more important, and we don't want that in this case. So we can address this easily by scaling the data within the PCA. So this is equivalent to that normalization step that we've talked about in class. That is the first step of the PCA, where we just shift everything to be 0. And this is how it's done. You just set scale equals true. And then if I run the biplot, you can see that it has changed dramatically. Now these loadings, the vectors right here, they are all more or less, they're very similar. And that makes sense because we have all normalized them to have a mean of 0 and a standard deviation of 1. All right, how to actually get to the output of the PCA? You need to call the PCA object that you created with the summary function that gives you all the detail you want. So running this gives us a whole lot of information. For example, there are some terms that you may recognize, eigenvalues and their contributions to the correlations. You now know what eigenvalues are. So you can see that we are explaining a lot of variance. We only have 4 axes here, keep in mind, but the first PC axis explains 55.6% of the variability in the data set. And you can see this cumulative proportion of variance explained right here, which is really nice. Now, mind you, the species in this data set or in this analysis are really actually the morphological traits. Now, this is a little confusing because vegan, being a package for community ecologists, automatically assumes that you're running this on a community ecology data set. So it says species scores right here, but these are just our morphological traits. So it takes a little bit of mental gymnastics here to envision why these are called species rather than traits in this case, when our species are really the sites. So here are the site scores, and there are your species. This will change later on. So this is really the most important bit of the summary. You've got your eigenvalues, you've got your species scores, and your site scores. So far so good. Here are a couple of exercises that you can do. And it uses the data set that is also on the companion page up on the link. It's called fishcoms_lizardisland.csv. And you can do the following. You filter it to include the family Pomacentridae and then summarize the abundance for each site and exposure regime. You then spread the data set based on species, with the missing values being replaced with zeros, and separate it into the abundance data and the metadata. And then you can run a PCA on the abundance data with scale equals true and call the summary. And here are the solutions. They don't need too much explaining. They're pretty straightforward. But you filter, you group, you summarize, and then you spread. Note that fill equals 0 here will replace all DNAs with zeros. Then you separate it into 2 components. And then you run your PCA, and this is what it looks like. So now you can, for example, see we're explaining a lot less variability on the first axis, 21.8%. And this time our species score are actually species, and our site scores are actually sites. Beautiful. Okay, so how do we visualize PCAs? R has an out-of-the-box plotting function that is useful but aesthetically terrible. It's the biplot function, so you can always just run this biplot lfish.pca. So lfish.pca is a PCA object that I ran earlier as part of these exercises. That is the lizard island data with the pomacentrid fishes. And you can see the sites are nicely spread throughout this ordination, and then we have this cluster of species that explains stuff. So the PCA in and of itself looks pretty good, but it's just ugly. The other one that comes out of the box is the scree plot, and that is a good way of visualizing your PC axis. So that takes the eigenvalues, the first part of that summary of the PCA object, and gives you this graph that shows how much variability you're explaining. In an ideal world, you always want a pretty steep sort of drop off across the first couple of PC axes. That suggests that the PCA does a pretty decent job. Okay, so you can improve the aesthetics of your biplot a little bit. If you like plotting in base R, be my guest. I can't do it for the life of me. I'm actually amazed I pulled this one off right here. This is base plot plotting. It turns it into a pretty decent graph. I'm not gonna lie, I don't mind this graph, but at the end of the day, I'm just so much more comfortable in ggplot that I'll always choose to use ggplot instead. But yes, so when you use ggplot, that requires a little bit of tinkering. So we have to take some of the outputs of the PCA and turn it into our own data set, because there's no inherent way for ggplot to do this. There may actually by now be a way of feeding actual PCA objects to ggplot, but if there is, I don't know. You can try to find out, but I'm not using them. So there are two main layers in the summary output that we're using for the plot, and they're the loadings, which are species, and the site scores, which we can access through a summary object. So what I usually do is I create an object that has the summary output of the PCA in it. And then I just create a data frame that has the sites of that output, that summary output file. And then I bind that or join it, depending on how you want to do it, with lfish.meta. So this is the metadata from this. And what this looks like is like this. So we have our sites, PC1, PC2, PC3, PC4, and so on and so forth. And we have our metadata that just gives us the site name and the exposure of whether it's sheltered, lagoon side, oblique, exposed, whatever. And then I can do a very similar operation with the species scores, where I take the species part from that summary output. And then all I have to do here actually is to create a column that's called species, and that is taken from the row names. That's very convenient with the species. And again, this gives me the PC axes scores for the loadings, as well as the species that is associated with it. When I plot this, you simply create a ggplot object. You have to re-specify these two different data sets, which is sometimes can cause some complications. You just got to be mindful of it. So I'm creating a ggplot object, and then I run geom_point, and I specify the data, which are my site scores. So the points right here are my sites, and they're taken from these site scores. Specify your aesthetics. X is PC1, Y is PC2, and then I'm coloring them by exposure. And then I use geom_text in this example, and I'm using the species scores, and again, X is PC1, Y is PC2, and then the label is the species, and you can see it plots the species names right here as the vectors. Then just some aesthetics, but this is kind of a nice graph. It just has a big old mess of species in the middle right there, which we can address. And one way of addressing that is by parsing out the most important loadings. So right now it just plots all the fish. We may just want to take out the ones that are more important. And you can do that by filtering your species data set by the absolute values on PC1 and PC2. You have to use the absolute values because obviously you have negative and positive values. And so by just saying, hey, I just want values greater than 0.5, for example, you would dismiss all of the ones that are actually important loading on the negative side of PC1. So what I'm doing here is I'm just filtering, and I'm filtering it by the absolute value of PC1 being larger than 0.5 or the absolute value on PC2 being larger than 0.5. The 0.5 value, look, I just came up with it. I looked at the data and I looked at it and I said, okay, well, it looks like, this is a reasonable cutoff. That can be anything. You just have to be, explicit about where you specify that to just create a better visualization. And this is what it looks like. The only other change I've made here is I have used the geom text repel geom in ggplot rather than geom text. The repel function is really useful. It's in the ggRepel package, so you might want to download and call that into your environment. And what it does, it basically just offsets things on a graph slightly to make sure that they're not overlying. And you can play around with that a little bit, but it's very, very useful. I highly recommend it. We can also make those labels a little prettier by using geom label repel instead of geom text repel. And we can add the little lines that are typical for PCA loadings. So the lines come from geom segment. For geom segment, you have to specify a beginning and the end. Because we always want them to come out of the origin, the 0, 0 line, we specify x equals 0 and x end is PC1. And then likewise, y equals 0 and y end is PC2. And for geom label repel, the only other change I've made here is the size. I've decreased the size a little bit, but it creates these nice little rounded boxes around the label. So generally aesthetically quite nice. Okay, and then finally we can add some polygons around our groups if we want to. The function that really helps us with this is the slice function, but we have to again create a new data set for our polygons. So you can call that hulls or something, and we use the site scores for these polygons because obviously they are based on the site scores. We group them by exposure, that's the important part, and then we use slice and then the chull function, which is a convex hull, and we want that to be run over PC1 and PC2. And what that gives us is this tibble right here. It has the outermost vertices of each exposure regime to draw these polygons around it. And this is what the output looks like if we implement that using the geom polygon function. So data is hulls in this case. The aesthetics are very similar. The only thing to be mindful of is you do want to specify a group argument, group equals exposure and fill equals exposure. Otherwise, you might run into trouble with the polygons. And then I'm just setting the alpha to be 0.5 to make them half transparent. All right, so far so good. We've played with little fish. So let's have a look beyond the simple PCA. Because PCA, as you would by now undoubtedly remember, can only really be used for certain types of data. And it's not actually appropriate for the data we just used, so we can do a lot better. For abundance data, the Hellinger transformation is a great start. And the Hellinger transformation is implemented using the decostand function. Decostand, again, part of the vegan package, is implemented right here. So we can call our object lizard.hell. Same data set we're working with. So we use decostand on the raw data, and we're telling it the method that we want to use is Hellinger. What you can see is what used to be count values, so like 5, 6 to 100, whatever, are now decimals somewhere between 0 and 1. Okay, that's what the Hellinger does. It brings everything between zeros and ones. And then we can run basically the same PCA we ran earlier, just with this Hellinger transformed data. So what I'm doing here is I'm just taking a little shortcut, directly running the summary of the RDA on lizard tail, scale equals true. And then this is all the same as we did earlier, so don't worry about that necessarily. And then we plot this, and it actually looks a lot nicer than it did earlier. So this is the same plot, same data, but Hellinger transformed in this case. This is a really nice looking PCA. I don't mind this at all. And it tells us a lot about the data. It clearly shows that these 4 exposure regimes, the sheltered, the lagoon, the exposed, and the oblique sites, differ in terms of the pomocentrid communities that live there, with the exposed sites being characterized by Chromis weberi and Pomocentris lepidositis. Pomocentris nagasakiensis is characterizing the sheltered sites, and so on and so forth. So that's really nice. We can also, in this case, unscale our PCA. So the rationale here is that the abundances of different species may actually be informative against each other, rather than just being a nuisance difference. So we're essentially taking into account that there are also differences in the abundances among species, not just within a species among sites. So if we run the exact same thing with scale equals false, so not normalized to a mean of 0 and a standard deviation of 1, we can see that our outputs change slightly. They still show that there is good separation, but you'll also see that some of these loadings have become much longer than the others, and that's what typically happens when you don't scale transform your data, because now some of these species load more heavily on these different axes. Okay, and then if we want to move beyond just Euclidean distances and implement a PCOA or an NMDS, we have to work with different functions. They can still all be implemented in the vegan package. So in this case, we're running an NMDS with the meta MDS function. And so we're running this on the raw data. We don't have to use the Hellinger transform data. We're specifying here that we want it in 2 dimensions, so k equals 2. NMDS is an iterative ordination, so it tries to find solutions, and you can specify how many times it gets to try. So in this case, we're letting it try 1,000 times, probably too much, doesn't need that much. And then we're using the Bray-Curtis dissimilarity here. And that is the best one to use, generally speaking, for abundance data sets. It's really good for that type of stuff. So you can see it has these different iterations, these different runs right here, and it finds new best solutions. And then it tries again, and it tries again, and it tries again. And this one actually stops after 20 because it feels like it has found a best solution. It actually stays here, best solution repeated 4 times. So it feels comfortable that it has found the best solution for this ordination. Some important information when you call the MDS function is here. So it actually does a bunch of other transformations. This is called a double Wisconsin transformation. It tells you the distance metric it used, it tells you the dimensions, and it tells you the stress. So this is all kosher. There is no red flags, no concerns here. If you look at the stress plot, which you can call right here, you can see that the blue dots are pretty well dispersed around the red line, so there's no real concerns there. This all looks pretty decent. Now for plotting the NMDS, the principle is the exact same as it was for the PCA. You just take these different elements that you get out of the MDS and turn it into data frames that you can then work with in ggplot. They're called slightly differently. That's the only thing. So you have points instead of sites, and then the axes are MDS1 and MDS2 instead of PC1 and PC2. Pretty simple. So then you can essentially do the exact same thing you did earlier. This is the output of the NMDS, and it looks really nice, looks really pretty. Again, you get the different species loading differently onto these axes that are now called MDS1 and MDS2. And you can still see very good separation of these sites based on their exposure regime in multivariate space. And that is essentially it for this part. This should give you the basic tools to dig into the ordinations yourself. And I hope you'll have some fun with that. And we'll leave it there.